This video is a second problem or second sample problem for electrochemical cells. Now let's read the problem. Consider a voltaic cell in which the following reaction occurs. So we have oxygen gas with a pressure of 0.98 atmosphere plus 4 hydrogen ion. So this is an aqueous solution with a pH of 1.24 plus 4 moles of bromine ion which is also aqueous with a concentration of 0.15 molars, and then proceeding with a product of 2 moles of water plus 2 moles of bromine liquid. Now, additionally, we are given with the voltage at the reduction cell as 0.039 volts. The voltage of the oxidation cell is 0.126 volts with the number of 4 moles of electrons. Now, for the first one is we're going to calculate for E or the cell voltage at 25 degrees Celsius. And for letter B, when the voltaic cell is at 35 degrees Celsius, the cell voltage is measured to be at 0.039 volts. Now we are going to calculate this standard voltage at 35 degrees Celsius. Again, please do not be confused with E and E not or E degrees. E stands for cell voltage. E naught or E degrees stands for standard voltage. Now let's proceed. The solution for letter A, we're going to use the following as the cell voltage is equal to standard voltage minus the gas constant times the temperature in Kelvin multiplied with the natural logarithm of the reaction quotient all over n multiplied with Faraday's constant. But since our letter A is at 25 degrees Celsius, we're going to use the other formula as the cell voltage is equal to the standard voltage minus 0.0257 volts multiplied with the natural logarithm Q all over N at 25 degrees Celsius. Now let's proceed. Okay? Do not be confused again with E and E naught. For E, it stands for cell voltage and E naught stands for standard voltage. Now, the standard voltage is equal to the sum of the voltages for reduction and oxidation. Now, let's substitute the following values as 0.039 volts plus 0.126 volts, which gives us 0.165 volts. And since we are given with the following reaction as oxygen gas with a pressure of 0.98 atmosphere plus 4 moles of hydrogen ion with pH of 1.24 plus 4 moles of bromine ion. Okay, this is in water, aqueous, at a concentration of 0.15 moles, forming a product of 2 moles of hydrogen or dihydrogen monoxide or water plus 2 moles of bromine liquid. Now, our O2 has a pressure of 0.98 atmosphere. To determine now the concentration of hydrogen ion, since we are only given with pH, so the formula to determine the concentration of hydrogen ion, H positive is equal to 10 raised to negative pH. Now let's substitute the following values to determine pH or to determine the concentration of hydrogen ion via pH. So 10 raised to negative 1.24. This gives us 0.0575 molars. Okay, the unit for hydrogen ion is in molars. Now, we are given with the bromine concentration at 0.15 molars. Since we are given with the following liquids, H2O would be equal to 1, no concentration. So for diatomic gases and substances and water, we're going to use the concentration would be equal to 1. Same goes with the bromine liquid as equal to 1. Now we're doing this to determine the reaction quotient. Okay? Since we are not given with any reaction quotient, to write now our reaction quotient, Q now is equal to the product all over the reactant. For this equation, Q now is equal to H2O squared multiplied with bromine gas squared all over bromine ion, which is the reactant, raised to 4, multiplied with hydrogen ion raised to 4, multiplied with oxygen gas raised to 1. So where did I get the following notations as 2, 2, 4, 4, and 1? So these are the balance coefficients for the following reaction. Okay? For hydrogen or water, since we have the balanced coefficient as 2, so H2O now raised to 2 or squared. Our bromine ion with a balanced coefficient of 2, Br2 raised to 2 or squared, all over the product of the following reactants as oxygen, hydrogen ion, and bromine ion. So for bromine ion, Br negative or Br minus is raised to 4 with a 4 balanced coefficient times the hydrogen ion, which is raised to 4 as well, multiplied with the oxygen gas, since the balance coefficient is only 1, so this is also raised to 1. Now, if we're going to substitute the following values, again, the concentrations for water and bromine gas or liquid or diatomic bromine, it is also equal to 1 because we are not given with any concentrations for those. Okay? So 1 squared times 1 squared all over the following. The concentration of bromine ion, 0.15, which is raised to 4, multiplied with the concentration of hydrogen ion, 0.0575 raised to 4, times the concentration pressure of oxygen gas, which is raised to 1. Now, our reaction quotient is equal to 1 squared times 1 squared all over 0.15 raised to 4 times 0.0575 raised to 4 times 0.98 raised to 1. This gives us a value of 184,390,061.6 for the reaction quotient. So this is unitless. To solve now for the cell voltage for letter A, let's substitute the following values. Cell voltage at 25 degrees Celsius, E is equal to E naught minus 0.0257 volts times the natural logarithm of Q all over N. Substituting now the values gives us 0.165 volts minus 0.0257 volts multiplied with the natural logarithm of 184,390,061.6 all over 4 moles. This gives us an answer of 0.0427 volts for letter A. Now let's proceed for letter B. B is when the voltaic cell is at 35 degrees Celsius, the cell voltage is measured to be at 0.039 volts. What is the standard voltage at 35 degrees Celsius? At 35 degrees Celsius, we're going to use the cell voltage is equal to the standard voltage minus the following fractional quantities as the gas constant times the temperature, which is 35 degrees Celsius converted to Kelvin, times the natural logarithm of Q all over N times F. Now, since we need to solve for the standard voltage at 35 degrees Celsius, we have to transpose this quantity negative RT ln Q all over NF to the other side of equation. So it becomes E plus RT natural logarithm of Q all over N times F. So the temperature must be in Kelvin. Now let's substitute the following values. This gives us the cell voltage E naught is equal to 0.039 volts plus 8.314 joule per mole Kelvin for the gas constant SI unit. Multiply it with the temperature. Take note, this must be in Kelvin or converted to Kelvin. So 35 degrees Celsius plus 273.15 kelvins times the natural logarithm of the one we solved earlier for Q at 184,390,061.6 all over 4 mole times 9.648 times 10 raised to 4 joule per mole volts. Okay, this quantity is the Faraday constant. Now, this gives us the value for our final answer at 0.1653 volts. Now, let's summarize the solution. Solving for letter A, first, we need to determine the standard voltage. E naught is equal to the sum of voltages for reduction and oxidation. And then we need to get the concentration of hydrogen ion because we are only given with pH. So hydrogen ion is equal to 10 raised to negative pH. And then let's go to reaction quotient. So this is the third step. Reaction quotient, Q is equal to the product all over reactant. And after that, after getting your Q, we may now substitute Q on this following equation for the cell voltage at 25 degrees Celsius, which is equal to the one we solved earlier, the standard voltage minus 0.0257 volts times the natural logarithm of Q all over N. Now, the summary for solving letter B, we're going to use this formula. E is equal to E naught minus RT times the natural logarithm of Q, the one we solved from letter A, all over N times F. Now, our cell voltage, if we're going to solve for standard voltage, transpose the following fractional quantities. So our standard voltage now is equal to the cell voltage plus RT natural logarithm of Q all over N times F. Please do not be confused with cell voltage and standard voltage. For A, it stands for cell voltage. For E naught stands for standard voltage. Our next video is a third example problem for electrochemical cells.